Good morning. I welcome the opportunity to be here in Paris as part of this opening ceremony, and I will say a little bit today about pulsars. It is 400 years since Galileo turned his telescope to the skies, but with pulsars it is just over 40 years. And perhaps the surprise was as great when the pulsars were discovered. I am aware that I have a very wide audience. I am going to pitch this talk to the students mainly, which means that I will bore some of the people some of the time, but I will also try and include some more advanced material, so I may lose some of the people some of the time. But you can't win them all, I think. Could we have the audio recording, please? No? Yeah. Thank you. The pulsar goes on forever, but we do not need to listen to it forever. That is the pulsar in the constellation of Vela. The pulsar that was formed when the Vela supernova took place 10,000 years ago. Here is a picture of that area of sky, although I have to say the pulsar is somewhere away off to your left. This is the edge of the material expanding out from the supernova. It is the remnant that is expanding out like this. And it will continue expanding and thinning, and in 100,000 years, it will be so thin that the remnant is no longer visible. But the pulsar will likely still be there. What you have heard sounds a little bit like a tractor or a truck, a roughly running tractor or truck. And there have been times when I wished it was just a tractor or a truck, but it is not. It is a star of mass comparable to the Sun, 10 to the power 27 tons, all spinning 11 times per second. It sounds like a truck or a tractor because the engine idles at about 700 revolutions per minute. And this object, going 11 times a second, is doing 660 revolutions per minute. 660 is close to 700, hence it sounds like a truck. Pulsars come with a variety of pulse periods, and we have next a rather faster one. Could we have the sound file again, please? This pulsar has a period of about 1.5 milliseconds, or a frequency of about 600 hertz. When you listen to this one, you do not hear the individual pulses, merely the note, the continuous note that they make. Look how precisely a pulsar period is measured. Many, many, many decimal places. And this figure here, the 4 at the end, is partly experimental uncertainty, but is partly because the period is gradually increasing. If you monitor this period for perhaps a year, you will see the 5 go up to a 6. So that's one element of that. This is no longer the fastest pulsar. There's been one discovered more recently with a period of about 1.4 milliseconds, a frequency of around 700 hertz. And then the question is, how fast can a pulsar spin? On our present understanding, the answer to that question is about this fast, about 700 hertz. Because it is believed if they spin faster, you get instabilities in the core of the pulsar. They're called Rossby mode instabilities, R mode instabilities. And these Rossby mode instabilities emit gravitational radiation, which effectively prevents the pulsar from spinning any faster. So now the hunt is on amongst the observers to find an even faster pulsar to see if we can knock the theory. But for the moment, that's where we are, close to breaking the theory, close to breaking that bit of theory. This is a simplified picture of a pulsar, but I believe it is useful for a start. You have in the center the pulsar, which is believed to be a neutron star, an object that is rich in neutrons, but not totally neutrons. And this pulsar spins about an axis like this. For the first pulsar you heard, it's spinning 11 times a second. For the second pulsar you heard, 600 times a second. You know that on Earth, the magnetic North Pole is not at the geographic North Pole. Magnetic North is in the north of Canada. Similarly, we think on a pulsar, the magnetic field is inclined. Magnetic north is not at the North Pole. We also believe that there is a very strong magnetic field, which here we have shown like the magnetic field of a bar magnet, but maybe that's too simple. And near the poles, the magnetic field lines form a cone or a trumpet. And from this area over the poles, we think the radio beam comes. And as the star spins, a radio beam sweeps round the sky. So they are a bit like a lighthouse swinging a beam round the sky. And I have a demonstration of this, which will need me to put the microphone down. I will try shouting. Can the back row hear me? Thank you. So here is a beam. As the star spins, the beam sweeps across the Earth, and we see a pulse. But we only see a pulse if the beam sweeps across the Earth. There are others that we never see. We believe we see 1 in 5 of all the pulsars. Only 20% can we detect. Pulsars are like lighthouses in another way. Each lighthouse has its own period and its own pattern of flashes. It seems that each pulsar has its own period and its own pattern of flashes. So, when we start interstellar travel, we can use the pulsars as navigation beacons. We have our spaceship, we have an enormous radio telescope, and with this enormous radio telescope, we detect pulsars. We say, yeah, that pulsar is there, that pulsar is there, that pulsar is there, so we are here. At the moment, it would not be technically very feasible. Rather than attaching a radio telescope to your spacecraft, you attach your spacecraft to a radio telescope. But the technology will improve. So maybe one day we will use these as navigation beacons through space. Thank you. You saw the accuracy with which a pulsar period is measured. Pulsars are very, very precise clocks. They are more precise than any watch in this room. A quartz watch is good to about 1 part in 10 to the 8. The typical pulsar is 1,000,000 times better, and the most stable pulsars, just a few of them, are better than the best terrestrial time standards. But the Americans are working on that because they don't like being beaten by nature. But because we now have clocks throughout the galaxy, we can do experimental relativity. And this has been one of the major uses of pulsars by physicists. A number of pulsars are in binary systems, twinned with another star, quite often with a white dwarf, sometimes with another neutron star, on one occasion with another pulsar. So far, we have not found a black hole pulsar binary, but we keep hoping. And because these pulsars are such good clocks, you can study Doppler shifts from the orbits. And I have a demonstration of this, which again will need me to put down the microphone. The demonstration is not entirely safe. Will people in the front please keep their eyes open? You have half of 1 second to duck. Okay? It's my kitchen timer. But today it is a pulsar. Today it is a pulsar in a binary system. This is a wonderful big hole. Can you hear the warble change the notes? The doctor.
Not so music.
This is a pulsar in a binary. We can use this demonstration for other things, and I will show you some more in a minute. Kepler told us about elliptical orbits. We know that classically there are 5 parameters we can measure. When you get into relativistic orbits, there are a further 5 parameters. And now with the double pulsar, the binary with 2 pulsars in it, in that binary, they have measured all 5 relativistic parameters as well. And now they go one stage even deeper. They have found the relativistic spin-orbit coupling. And I hope soon we get an independent estimate of the moment of inertia for a pulsar, because that will be useful too. We've heard a lot, and very interestingly too, about planets around solar-type stars. The first extraterrestrial planets were actually discovered several years before those. They are pulsars round a planet. And they've been detected again by the Doppler shifts. As the planet orbits the pulsar moves just a little bit, and the radio astronomers can detect that Doppler shift. We know of 4 planets around that particular pulsar, 2 of them that are 3 or 4 times the mass of the Earth, and 2 lighter ones. There are many pulsars in globular clusters, but the stellar history in globular clusters is confused. The stars are so closely packed that there are many interchanges in the binaries. There is wife swapping. And sometimes the new wife comes with a child, a planet. So in a couple of cases of pulsars in globular clusters, we know that those pulsars have planets, but we think they are not original planets. But we have one pulsar where there clearly are planets, and it is an isolated pulsar. We know of about 2,000 pulsars in total. Why does one have planets? Why does only one have planets? I can think of many reasons why there should be no planets. Red giant expansion, supernova explosion, highly radiative beam from a young pulsar. Okay, we have one. Maybe our theory is incomplete. Maybe there's more theory needed. But why not several? Why just one out of 2,000? I find that a very big puzzle. I'm now going to teach you general relativity, students, without equations, in about 2 minutes. And apologies to the professionals in the field for this bastardization of the subject. One of the predictions Einstein made, coming from his theory of general relativity, was that there would be a form of radiation called gravitational radiation that is emitted when a body accelerates. So when you drive away from the traffic lights in your car, you are emitting gravitational radiation. As the Earth goes around the Sun, it emits gravitational radiation. As a pulsar in a binary goes round its star, it emits gravitational radiation. And the pulsar emits the most of those three examples. The gravitational radiation carries away energy, and when a binary system loses energy, the two stars move closer together. The acceleration is greater, they go round faster, there is more gravitational radiation, there is more energy loss. The two stars move closer together, the acceleration is greater, there is more gravitational radiation, there is more energy loss, and so on. And the two stars will spiral in. And again, I abandon the microphone to demonstrate this. So here is our pulsar, the binary system, pre-Einstein, with Einstein, spirals in, faster and faster and faster and faster and faster, and merges. And the graph on the screen shows the work of Taylor and Hulse studying the orbit of the first binary pulsar discovered, for which they got a Nobel Prize, very rightly. You will see that the observations have taken place from about 1974 right until now, that initially there were measurable error bars, but that by now the error bars are about 2% of the size of the dot. The line, excuse me, is not the best fit. The line is Einstein's prediction. And so far, in spite of all our testing by pulsar astronomers, Einstein's theory is standing up very well. But we haven't given up yet. Another thing you can do with this timing and the study of orbits is to come up with some curious facts. The roundest known thing in the universe is the orbit of a pulsar round its companion star. The orbit is round to 1 micron, 1 micrometer in the radius of the orbit, 100,000 kilometers. mentioned the magnetic field that these stars seem to have. For those technically inclined, the magnetic field is calculated assuming magnetic dipole radiation. The assumption may be a bit wrong, but is not wildly wrong. And it gives us magnetic fields of about 10 to the 8 Tesla for pulsars, 10 to the 11 Tesla for the magnetars. We don't know what the shape of the magnetic field is, although most magnetic fields look like dipoles at a distance. We don't know how the magnetic field is created. We don't know how it is sustained. And since there's hints of superconducting material inside the star, that is serious. The pulsars are also weak emitters of radio waves. If you go on the Paris metro and get one of the individual tickets, when you pick up that ticket, you use 1,000,000 times more energy than a radio telescope receives from all the known pulsars in 1 year. The fluxes are weak. We have difficulty seeing pulsars on the far side of the galaxy with our present telescopes. With square kilometre array, we'll see all the pulsars in our galaxies. Although we understand fairly well how the pulse period is sustained by this business, the star rotating, we are less clear how the radio wave is generated. We still believe it comes from the magnetic pole, but our understanding of the production is described as second-order hand waving. The theory involves a lot of this. A very recent discovery has been of intermittent pulsars. It goes like this: pulse, 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 pulse. It always keeps phase. However you make a pulsar beam, how do you stop it? How do you reflect it? Where's the signal gone to? A big puzzle. One of the amazing things about pulsar astronomy is it is still delivering surprising results. It refuses to mature. It's still behaving like an energetic child. And it's great fun for that reason. Thank you. I've already mentioned that the mass is about 10 to the power 27 tons. The radius is only 10 kilometers. And I do not mean 10 to the power something kilometers. I mean 10 kilometers. So the density is phenomenal. The density, average density of a pulsar is like the density of the nucleus of the atom. And one way to visualize that is to take a sewing thimble, like this, and take the population of the world, the 6 billion people, and squeeze the 6 billion people into the thimble. When you have all 6 billion people in your thimble, it weighs as much as it would weigh if it were made of neutron star material. So there is some amazing physics because of these very high densities, as well as very high magnetic fields and very high velocities. One of the other intriguing things is there are some hints of higher mass neutron stars. Most of them are about 1.3, 1.4 solar masses. There are hints of some at 1.8, 1.9. Those might not be neutron stars. They might have to be quark stars or something else. But we'll wait until the mass is really determined. One of the results of having these high-density objects is physicists have done a lot of work on the behavior of material at these high densities. Very condensed matter physics. And it's pretty exotic. I haven't time to go into this in detail, and let me say it's not the only model, but this model involves a very thin outer solid crust, polymerized iron, with a Young's modulus about 1,000,000 times that of steel. Inside that is some neutron-rich material. Beta decay is prevented in this environment. Nuclei that would be radioactive here on Earth you can find in this layer. Inside that is a layer of neutron superfluid material. The standard BCS theory of superfluidity, only with neutrons. In the core, we are at densities far above nuclear. We do not really have adequate data. We do a lot of guessing. You can have Bose-Einstein condensates, you have kaons, pions, quarks, almost anything you wish in the center. Another consequence of the very strong density is very strong gravity. If I were to go to a neutron star, if, not recommended, but if, and if I were to drop a coin, it would hit the surface traveling at 60% of the speed of light. And it doesn't really matter where I drop it from, the acceleration is all in the last meter. The physics is very exotic on these objects. I think I'm going to skip this because I'm running short of time. Just to take you through the text on the right-hand side, we believe pulsars are formed in supernovae explosions. We can see how they move through this kind of diagram, which is a plot of their period against their period derivative. A big puzzle, a contemporary puzzle, is the pulsars up on the top right of that graph, which are known as magnetars, with very large magnetic fields. They're discovered by the X-ray astronomers. They look just like radio pulsars, except they don't pulse in the radio, and they have this very large magnetic field. The pulsar field is a field that seems forever young. It keeps reinventing itself. You think, how very interesting. And suddenly it delivers a jolt that wakes you up again. And this has happened time and time and time again. I think for me, the areas that are of interest at the moment are these highly magnetic neutron stars, the magnetars. I think the intermittent pulsars are absolutely fascinating. I've always been keen on transient objects, and these are transient objects with bite. There's a lot of testing of general relativity and its alternatives going on. Watch that space. And also look out for the direct detection of gravitational radiation. In addition to the well-known gravitational wave interferometers like LIGO and Virgo and GEO, there is another technique using pulsar arrays, monitoring the timing of the pulsar to detect the motion of a pulsar as a gravitational wave goes by. I'm not sure which of these two techniques will first find gravitational waves, but I think it's coming soon. Thank you for your interest.
Thank you.